The volume of a cylinder of height 11 inches and radius r inches is given by the formula V equals 11 pi r squared. What is the correct expression for dV dt? So the thing that students often make a mistake on here is they see this type of notation and they say in their minds derivative. Great. What they stop and what they don't stop and look at is the variable for which you are differentiating with respect to. That's really important. We're differentiating the variable v with respect to t. If you'll notice, the variable t does not exist in this expression. So we aren't just going to say, actually, I'm going to write it in red because it's wrong. We aren't just going to say dv dt equals 11 pi, and then this would be 2r, and call it a day. Because then it looks like 22 pi r, which again is in red because it's wrong. And the reason, uh, oh, funny, that's not even an option over here. That's usually the most common incorrect answer. The reason is we differentiated v with respect to the variable r. That's completely different for differentiating v with respect to the variable t. Now, what we have to do that's correct is assume that both v and r change with respect to time. So the volume of this cylinder uh, changes with respect to time, and the radius changes with respect to time. Okay, so we are going to differentiate this expression implicitly. So we use implicit differentiation to differentiate this with respect to the variable t. So what will that look like? Starting with the v. When I differentiate a variable v, it's a linear variable, and the derivative of a linear variable is just 1. So that's 1 times the derivative of the inside part. The derivative of the inside part is the variable v differentiated with respect to t. So this does turn into dv dt. All right, but something a little bit different happens on the other side. 11 pi is, of course, a constant. We can just leave that off to the side for a second. And now that brings us to the r squared. So the r squared, we are going to differentiate with respect to t. So we have to treat r squared as an outer function. We differentiate it as 2r. But according to the chain rule and how we work through implicit differentiation, we then must multiply by dr dt to complete the chain rule, which means dv dt is, in this case, 22 pi times r dr dt. So there are two different variables that involve derivatives. Derivatives are rates of change. So we have an expression that relates two rates together. That's why this section is called related rates. You're going to have more than one derivative in your answer. If you don't, you're on the wrong track. All right, so then now we can choose the correct item, which looks to me like this one right here. So all the rest of those are incorrect for some reason or another. Now, the next item here says, suppose that the radius is expanding at a rate of 0.4 inches per second. How fast is the volume changing when the radius is 2.3 inches? Round to at least 2 decimal places in your answer. Well, you might be thinking to yourself, how in the world can you have a cylinder that changes size? Well, honestly, I don't know. It's probably not made of metal because that would be kind of difficult to have an expanding metal unless it was, I don't know, being heated or something. But the thing is, it's a simple geometric object, and if we made it something that probably made sense within the realm of the real world, quote unquote, the mathematics would probably be so much more difficult that it is unreasonable to ask in an elementary calculus class. So just roll with it. We've got a cylinder that can change size. It's magic. Magic cylinder. All right, now, using this magic cylinder that can change, what we need to pay attention to is the language of calculus. The language of calculus includes things like rates of change. Rates of change are derivatives. In physics, the language of calculus are units of measure that are something with respect to time. So like velocity, it's meters per second is, or feet per second, or miles per hour, what have you. You have some measurement of distance changing with respect to time. That means that speed, velocity are both derivatives of something. They're derivatives of position. That's the language of the calculus. So when we read this, suppose that the radius is expanding at a rate of 0.4 inches per second. So we have the radius of this cylinder changing in a measurement of time. This tells me that this is a derivative. So the derivative, dr dt, the rate at which the radius changes with respect to time, is 0.4 inches per second. And you generally don't have to worry about units in a calculus class, but units can be extremely helpful in making sure you've got your formulas correct, because if the units don't match up on both sides of an equation, that tells you right away that you've got the wrong equation. How fast is the volume changing? So there's another thing about derivatives, because we want to know how fast the volume is changing. So that is telling us about a derivative. So this is dv dt, the rate at which the volume changes. And then it says when the radius is 2.3 inches. This is telling us a specific measurement. So it's saying that the radius of this thing is equal to 2.3 inches. All right, now let's try this out and see if things work out as expected. So we have our derivative, dv dt equals 22 pi r dr dt. All right, now we're looking for dv dt. It didn't give us a value for dv dt. It wants us to solve for that. So that means I'm going to plug in a specific value of r, which in this case is 2.3, and then the rate of change of the radius. So the rate of change of the radius is constant. So it's always changing at 0.4 inches per second. That's happening throughout time. But we want to know how fast the volume is changing, because the volume changes differently with different respects to time, or different points in time. So when the radius is 2.3 inches, how fast is the volume changing? So this would be solved. We can just use the calculator in order to get an approximation. That's perfectly fine. Let me make that a little bit larger here. So 22 times pi times 2.3 times 0.4, and that would be 63.59. It says at least 2 decimals. So 63.59. What unit would this be? Well, this is a volume. Volumes are cubic values, and it's still measuring with respect to time. So our time measurement was in seconds. so cubic inches per second. Now, the last thing I mentioned was about the units telling you if your problem has worked out properly. And the units here match up because here's the thing. Uh, the volume is, of course, inches cubed per second. So we have something measured in inches cubed per second. This 22, it was originally, it comes from a cylinder of height 11 inches, which is a constant value. But that 11 inches is measuring inches. And then the pi comes from just the volume of the cylinder formula. Pi is a unitless measure, so it doesn't really matter. You don't need to put pi in here. But we have something measuring in inches. Then we have our radius. The radius is also measured in inches. And right there, our units aren't matching up because I wrote it in red and erased it. But if we didn't have the dr dt over here, we would have something measured in inches cubed per second equaling something measuring in area, which is square inches. But if we multiply that by dr dt, which measures in inches per second, look what happens. 3 inches, or inches times inches times inches, that's cubic inches. And we still have per second. So the way that the measurements work out passes that test there. So at least the units match up, and we can be a little bit more confident that the answer is correct with that respect.